It's pretty wild to think that even a simple walk around the block is packed with some pretty complex physics. If you're a Class 9 student, you know exactly what I'm talking about. So today, we're going to crack the code of the motion chapter, which I know can be one of the trickiest parts of your syllabus. Let's get right into it. Does the whole idea of calculating distance and velocity and acceleration just make your head spin? Hey, you are not alone, trust me. These concepts can feel kind of tricky, but once you crack the code, they're actually a lot simpler than they look. And that's exactly what we're going to do today. We're going to take real questions straight from your sample papers to tackle the most confusing parts of motion. The goal, to get you feeling super confident and ready for your exams. Okay, first things first, we've got to clear the air on what is probably the biggest source of confusion in this whole chapter. It's the difference between two words that sound super similar but mean totally different things. So let's start with distance. The easiest way to think about this is like the odometer in a car, It just clicks up every single meter you travel, no matter which way you turn. It's the total ground you've covered. And because it's just a number, how much, not where, we call it a scalar quantity. That's it. Simple. Now, displacement. Displacement is like the cool, super efficient cousin of distance. It could not care less about the scenic route you took. All displacement cares about is the straight line from where you started to where you finished. It's that as the crow flies path. And since it has both a size, how far, and a direction, it's what we call a vector quantity. Okay, so here's where it gets really interesting. Imagine you walk all the way around the block and you end up right back at your own front door. You've definitely walked a certain distance, right? Maybe 400 meters. But what's your displacement? Well, it's a big fat 0. Why? Because you ended up exactly where you started. Your distance is 400 meters, but your displacement is 0. That's a huge difference. And this leads us to a golden rule that you are absolutely going to see on your exams. Just think about it for a sec. The shortest path, your displacement, can't possibly be longer than the actual path you took, can it? So displacement can be equal to distance, but only if you travel in a perfectly straight line. It can never be more. And that's why the ratio of displacement to distance is always 1 or less than 1. All right, let's move on to the next big challenge, reading graphs. You got to remember, these aren't just random lines on a page. They're actually telling a story about an object's entire journey. You just have to know how to read it. So check this out. This is a classic distance-time graph. The secret here is all in the slope, or the steepness of the line. The steeper the line, the faster the object is moving. So looking at this, who's the fastest? It's clearly car C, with the steepest line. And who's the slowest? Poor car B, just kind of lagging behind with the flattest line. But wait, you've got to be careful. Now look at this graph. This is a velocity time graph. That flat, horizontal line does not mean the object is just sitting still. Nope. It means its velocity isn't changing. It's cruising along at a steady, constant speed. We call that uniform motion. And this, right here, is the #1 most important rule for these problems. Before you even think about interpreting a graph, look at the labels on the axes. Are you looking at distance versus time, or velocity versus time? Because that one little detail changes the entire story. All right, now for a question that trips up so many students. It looks really simple on the surface, but it actually hides a super important, deep concept about what motion really is. So picture this. A boy is on a merry-go-round, and it's moving at a perfectly constant speed, say 10 meters per second. The little speedometer on his ride doesn't budge. So is he accelerating? What do you think? Now, before you give your final answer, let's just go back to the official definition. Acceleration is the change in velocity. And what did we say earlier? Velocity isn't just speed. It's speed and direction. Both of them. So the answer is a huge yes. He is absolutely accelerating. Even though his speed isn't changing, his direction is changing every single moment as he goes around in that circle. And because his velocity is changing, he is accelerating. This is a game changer of a concept. Circular motion is always accelerated motion. In fact, that specific pull towards the center has a name. It's called centripetal acceleration. Okay, we've covered the core concepts. We've talked about distance, displacement, graphs, acceleration. Now let's roll up our sleeves and apply all of it to a full exam-style numerical problem, step by step. So here it is, a classic 2-part problem you might see on an exam. A car speeds up, and then it holds that speed. We're going to need our trusty equations of motion to break this down and solve it. Let's just tackle this one step at a time. For the first part, those first 8 seconds, we use the formula S equals ut plus half at squared. Now, the car starts from rest, so our initial velocity u is 0. That makes it easier. So distance is just half times 5 times 8 squared. That works out to 160 meters. Okay, part 1 done. Now, how fast is it going at that point? We use v equals u plus at. Again, u is 0, so it's just 5 times 8, which gives us a velocity of 40 meters per second. Perfect. For part 2, the car travels at that constant speed for the next 4 seconds. For that, distance is just velocity times time. So 40 times 4 gives us another 160 meters. Now all we have to do is add them up. And the grand total distance is 320 meters. See? When you just break it down into smaller pieces, even a problem that looks complicated becomes totally manageable. That's the real secret to acing physics. So, let's just quickly recap the 3 biggest ideas we covered today. Number 1, displacement is the shortest path. Distance is the total path. They are not the same thing. Number 2, always, always, always check the axes on a graph to understand the story it's telling you. And number 3, acceleration isn't just about changing speed. Any change in direction is acceleration too. And before we go, I want to leave you with a little brain teaser to think about. If you drop 2 objects from 2 different heights, but at the exact same time, what happens to the gap between them as they fall? Does it stay the same? Does it get bigger? Or does it get smaller? The answer might surprise you, and it has everything to do with the constant acceleration of gravity. Give it some thought. Thanks for tuning in.